Okay, problem 5 here is from a test from 2 years ago, from 2000, fall of 2010, right? And it was probably too hard, but hey, that's what made it fun, right? So, I mean, what's the point of being a teacher if you can't occasionally torture your students? So, we have Mr. Rose and me standing on the edge of a cliff with a height of h. I'm going to go ahead and draw that in here. And, well, that's probably a little low for the cliff. I'm just going to draw one person here, and you can pretend it's the two of us. Oh, why not? There we are. Mr. Rose is, I don't know, looks like he's wearing a skirt or something. He doesn't normally do that. Anyway, so at the same time, Dr. Smith, that would be me, throws a rock directly upward at a speed of v0, and Mr. Rose throws a rock directly downward at the same speed v0. So we want to show that both rocks hit the ground below the cliff with the same velocity. And then we want to find how much time passes between them hitting. And then it's plug in some numbers. I'm just going to get rid of the plug in numbers part because I think that's pretty easy. And you guys should know how to plug in numbers. So showing that both rocks hit the ground with the same velocity. Now there are two ways to go about this. I'm going to show you the straightforward sort of the plug and chug way first, and then I'm going to show you the somewhat more artful way. So if we want to plug in numbers here, what we need to do is say we need to define which way is positive and define our variables here. So I'm going to say this direction is positive y. I'm going to say right here is y equals 0. Okay, that's the bottom of the cliff. And we start at y equals h. Okay, so that's where the rocks start. Now, Mr. Rose's rock starts here, and it has, well, it just goes down and hits the ground. So for Mr. Rose's rock, state 1, its initial velocity, so v1, is going to be, it's got a speed of v0, and it's initially going downward, but it's always going downward. So that is negative v0. And then v2 is, what we want to find, so question mark there. And Mr. Rose's rock, so I'm going to do like a little R with a circle here to indicate that that is Mr. Rose's rock in purple. And delta y for Mr. Rose's rock, so it starts at y equals h, ends at y equals 0, so it goes through a change of h, and it's a negative change because it goes from h to 0. So delta y equals negative h, okay, for Mr. Rose's rock. Finally, what's the acceleration of Mr. Rose's rock? Well, it's accelerating due to gravity, and as a general rule, when you're doing problems like this, you want to leave, if everything else in the problem is symbolic, like, v0 is symbolic and h is symbolic and all, then you want to leave, if acceleration is equal to negative g, for example, you want to leave it as negative g. So because you're accelerating this way, okay, accelerating down, that's the negative y direction, so acceleration is negative g. So for Mr. Rose's rock, what we're going to do is we want to find this final velocity. We have the initial velocity, we know delta y, and we know acceleration. So the equation that works for us here is we go v final squared, which is going to be v2 squared, minus, and then our initial velocity, which is negative v0 squared. Okay, we take that whole thing and multiply it by 1/2. Okay, and that is going to equal, that equals a times delta y, right? So this is going to be g times h. Okay, that's just taking the equation here. I'll write it really quickly up here. Vf squared minus vi squared. Okay, 1/2 of that equals a times delta x. Okay, and so that's just applying this to the Rose situation. Okay, now for Smith, my rock goes, well, it starts, I mean, I can't really draw it because I've used up too much space over there, but it starts here, initially going upwards. So for Smith's rock, v1, velocity at state 1, which is right here, is going to be positive v naught, and then it goes up, and then it comes back down, and I'm going to go just to and you'll see why in a minute. I'm going to leave a few spots in here, and I'm going to make this point here 0.4. So when it hits the ground, V4 is what? Okay, and that's going to be the same as its final velocity. Okay, so we have to find that the green V4 is equal to the purple V2. Yeah, sorry, probably not the best notation choice, but whatever. So what we also need to find here, before we can do that, is we need to find the total displacement my rock that goes through. Now here's the thing. My rock starts at this spot here, which is y equals h, right? Just like Mr. Rose's rock. My rock starts in the same place as Mr. Rose's rock, and it ends at the same place as Mr. Rose's rock. So that means my rock goes through the same displacement as Mr. Rose's rock. And this is sort of a test of whether you really get what displacement is. My rock, so delta y is going to be, from 1 to 4, is going to be y at the end minus y at the beginning. This is how we do change of anything, okay? So delta y is change of position. So y of 4 is 0, and y1 was h. So your displacement from 1 to 4 is negative h. Okay? So then the other thing is the acceleration. And since I'm using the same coordinate system here and the same a, so my acceleration is down, so acceleration is also equal to negative g there. Okay? So now, for applying this to this equation here to the Dr. Smith rock, we get 1/2 times v final, which I'm going to say is v4 squared, minus, and then my initial velocity was positive v naught, so v naught squared, okay, equals the acceleration, which is negative g, times delta y in this case, because we're using y, which says negative h. So that equals g times h. Okay? Now what you will notice here, so let me just outline these in red here. Okay, this is the equation we sort of got when we plugged everything in for 3, and this is the equation we got when we plugged everything in for, I'm sorry, for 3. Why did I say 3? I guess my S looks sort of like a 3 if you're blind, which apparently I am. Okay, so, but the equation for Smith's rock and the equation for Rose's rock, well, the only difference, I mean, you know, we have V2 for Rose's final velocity and V4 for Smith's final velocity, but that's just because we chose different things, different numbers of states, okay? So the only difference is we have this negative V naught that gets squared, and here we have the positive V naught that gets squared. But as you should recall, if you square a negative number, it becomes positive anyway, right? So negative V naught squared is equal to V naught squared. So this here in this parentheses squared equals this here, which means that, and since g and h are the same, Rose's final velocity, or the Rose's rock's final velocity, is equal to Smith's rock's final velocity. And if you want to say that in sort of a mathy way, you can say, let me see if I can scoot down just a wee bit. Yep. There we go. Okay. So what you could say is, by inspection, and I guess if you're going to say V2 equals V4, you really ought to like specify which one. So velocity of Rose's rock final is going to be equal to velocity of Smith's rock final. And it's by inspection is just math speak for, you know, come on, look at it, it's the same. You need to sort of work it. You need to work the algebra to the point where it is obvious when you point it out, but if you say it by inspection, it's almost like, you know, come on, it would be insulting for me to actually go through and you know, prove this to you. Just look at it. It's obvious. Okay? So that's what by inspection means. Now the other way to look at this, a completely different way to look at the problem, is to, and I'm going to see if how much I can erase here, so I can reuse some of this. Whoops. Scary. Okay. So let's cut, and then that's actually not bad. Okay, cut. Okay, so let's just look at, now I'm going to do purple for Rose again. So Rose's rock, what he does is it starts and it goes down, and it starts initially with a speed of, so v equals negative v naught. Smith's rock goes up and then down to the bottom, and I drew the break there for a reason, you'll see in a minute. So Smith's rock starts with a velocity of positive v naught. If I said, I meant Rose's rock starts with a velocity of negative v naught. I'm not sure what I said. But here's the way to think about it. Smith's rock goes up and then it comes back down, and it has to pass through this level where y equals h, right? So this line here, and the rocks aren't actually moving horizontally, I'm just drawing them sort of arcing like that to fit it in the space, but really they go up and down at the same spot, or the same horizontal location. But the point is, if I can just stop, trying to explain things that don't need explaining, Dr. Smith's rock starts here, goes up, and then comes back down. And when it comes through here, when it passes back through this height again, what's its velocity going to be? Well, it's going to be the same as the velocity when it started, except in the opposite direction. So when Smith's rock goes through here, it's now going to have a velocity of negative v naught. Okay, so you see what happens? It goes up and comes down. All it does really is changes the sign of its velocity, and then it comes back down through this y equals h level. And at that point, it's as though it's starting there, like it's starting going down with an initial velocity of negative v naught, just like Mr. Rose's rock had. What that means is both rocks will then follow the same trajectory. And so therefore, whatever velocity Mr. Rose's rock has when it hits the ground, Smith's rock will also have. So if you sort of look at it this way, it's sort of clearer to see, and to me that's more satisfying than working the equation and seeing that these two equations are going to lead to the same result. Because you can look at the equations and say these lead to the same result, but it still doesn't really tell you why, or it doesn't tell you what's going on physically. This tells you what's going on physically. The reason you can think of it as the reason why they both hit the ground at the same time is because they both started at the same height and going in the same, at the same initial velocity. And I am almost out of time, so I'm going to have to, I'm a little worried about the length of this video, so I'm going to do a part B for problem 5 in just a second.